All right, before we move into talking about types of isomers in inorganic chemistry, let's look at a few examples in organic chemistry where it'll be a simpler start for us. So we have these three molecules here at the top of the slide. All three of these have the same empirical formula, C2H2Cl2. But these are three different isomers all having that same formula. But they're different types of isomers. So the first two that we have here, if I were to use the language to describe how this molecule looks, well, the carbon here on the left is attached to a carbon, a hydrogen, and a chlorine. This other carbon is attached to a carbon, a hydrogen, and a chlorine. And I would use exactly the same words to describe the second one. This carbon is attached to a hydrogen, a carbon, and a chlorine. Hydrogen, a carbon, and a chlorine. So we have the same types of attachments for these two. Well, then let's compare 2 and 3. Well, this carbon here on the left is attached to a carbon, a chlorine, and a chlorine. And those aren't words that we said for either of these first two. So this is definitely a different type of isomer. This one all has the same type of atom attachments, but different orientations in space. But the first two differ from the third one by how they're attached. So if we have two or more molecules with identical formulas, they're some type of isomer. Are the bonds the same? Well, the first one and the second one, the answer is yes. For the third one, the answer is no. Because, for example, this carbon is bound to 2 chlorines. This carbon is bound to no chlorines. And so this we would call in organic chemistry, this is the 1,1 dichloro, whereas these are 1,2 dichloroethanes. Well, or we can also call this a CHEM dichloride, since this is geminal substitution of the 2 chlorines on the carbon atom. So this is a constitutional isomer. These first two are stereoisomers of one another. This one being the cis, because the 2 chlorides are on the same side. This being the trans, because the chlorides are on opposite sides of the double bond. All right, so we do the same type of thing for inorganic molecules. So we go, and to be a type of isomer, they have to have exactly the same empirical formula. Then go and say, are the bonds the same, yes or no? If yes, then we get into this idea of looking at different types of isomers over here, which are stereoisomers, geometric isomers, or enantiomers of some type. If the answer is no, then in inorganic chemistry, we actually have 3 types that we'll talk about later, which are ionization isomers, linkage isomers, coordination isomers, and hydrate isomers. But for this lecture, we're just going to focus on this left-hand leg. So stereoisomers. For 4 coordinate, the 2 most common geometries are tetrahedral and square planar. For tetrahedral, we can have stereoisomers that work just like in organic chemistry. With a tetrahedral center, if we have 4 different groups attached, and this copper has chloride, bromide, water, and ammonia attached, then we have this configuration, and we have the non-superimposable mirror image. Okay, there's nothing like cis or trans that happens here. And if we have four different ligands bound, it's chiral, like the example that we have here. For square planar, we do now have cis and trans. And I will just choose to focus on the chlorides here. If I look at the 2 chlorides, if the chlorides are close as possible together, they're 90 degrees apart, it's the cis orientation. If they're as far apart as possible, it's the trans orientation. If we have a chelate ring, so something like the ethylene diamine ligand that we talked about earlier, that's going to dictate that we only are able to form the cis isomer because the ethylene diamine, its distance doesn't allow the nitrogens very far apart. And so the cis isomer has the nitrogens close, the trans isomer has them very far apart. And so in general, if we have a chelating ligand, we get the cis isomer only. For square planar, there's no chiral isomers if the molecule has a mirror plane. Here's a couple of funky ways of getting something that is chiral, that's square planar, but these are specially designed ligands where the chirality is really coming from the ligand backbone, so it's more of an organic type of chirality. The really new terminology that we're going to introduce for these coordination complexes is what happens when we have a metal with 3 ligands of one type and 3 ligands of another type attached. And that happens here with this cobalt complex that has 3 ammonias and 3 chlorides attached. The 3 chlorides can be in what's called a facial arrangement, and that is the 3 chlorides are as close as possible to one another. They're all mutually 90 degrees apart. That's the facial configuration. Or they are in the same plane. So these 3 are in the same plane, where this chloride and this chloride are 180 away, and then this chloride and this chloride is 90 degrees. This chloride and this chloride is 90 degrees. This is the myriadonal configuration. And then here's another molecule. We have cobalt with 3 ammonias and 3 nitrite ligands. Here is the facial arrangement, shown really nicely here. They all lie on one face of the octahedron. They're as close as possible to each other. And then here is the myriadonal configuration where 2 of the ligands are 180 degrees apart from one another. Notice over here, none of the ligands are 180 degrees apart. They're all mutually 90 degrees apart.